Hello everyone. In this video we're going to be taking a look at the graphs of exponential functions, what they look like, how to make them, and how to write them given a completed graph. Alright, and we're going to get started by looking at the how-to behind graphing before we actually graph one. This boils down to creating a table of values using your TI-84 graphing calculator. Now, a few of the values are going to be decimals, something like a half or a quarter, so we may need to approximate. These are from Desmos, but when we complete our graphs, we should put arrows on both sides because they do continue on forever. There is no point where this graph stops or is undefined, like we'll see with radical graphs later on. And notice the star down here. It says, for lack of a better word, hover, what we're going to later define as a horizontal asymptote. Hover above the x-axis for non-translated graphs. So there's a lot to unpack there. First of all, we haven't really learned what a translation is, but it's basically a graph that can be shifted up or down, left or right. So it's saying for a graph that hasn't been moved down, because obviously it would pass the x-axis in that case, but for your normal graph, notice here, it almost looks like it's literally on the x-axis. If we zoomed in, we'd see that it's increasingly getting closer and closer. And we'll talk a little bit more about why that happens in class. So things we don't want to do. A very common mistake when someone's completing, again, like a parent function, a generic exponential function, is to do something like this. Maybe they connect it quickly. This would be wrong for several reasons. So we want to make sure that it does not pass through the x-axis. It's kind of hovering right above. First of all, those values are going to be very, very small anyway, so we're not probably going to be going much to the left anyway. But some useful notes before we actually take a look at how to complete a exponential graph. All right, and we're going to graph probably one of the more common textbook examples of an exponential function, 2 to the x power. So you see, I have a 3-column table here. I'm just going to do my work in the middle, but our function is f of x equals 2 to the x power. So I'm going to create these points by hand, very simply, and if you have it in front of you now, you can enter this into your calculator. Be careful, after you hit 2, you want to hit the little caret button to create our exponent of x. Typing in 2x is obviously just going to give us a straight line. So 2 to the x power. So I'm going to start just by showing how these values would come out. It's a weird looking 2. And again, obviously, you just be copying down. You can also see what's nice about the graphing calculator. You can see why we're not choosing some of the other values here. Why does my table happen to go from -2 to 3? Even -2 is going to be almost very, very difficult for me to plot. 2 to the -2 power is 1 over 2 squared, or 1 over 4. So this is going to be -2 and a quarter, 0.25. That's very hard to plot on a normal graph. -1 is going to be 1 over 2 to the first, or a half. A little bit easier to plot. Anything to the 0 power is 1. And then we have 1, 2, 2, 4, and 3, 8. Now, why, if you scan up and down, did I not include other values here? Anything above -2, we're getting into 1/8, 1/16, very, very small. It's going to continue on. After I plot that point, I could just kind of, like I mentioned on the previous slide, hover and put an arrow. Anything above 3 is going to start being like 16, 32. Remember, we're multiplying by 2 here, so that's going to be very large, very difficult to fit on a graph. So if I plot this, I like to start with the y-intercept. We could have noticed that the y-intercept was 1 before we even started the table, because there is no a value out front. We just have our common base of 2 there. So there's really a value of 1 out front. That's our a value. That's right at 1. Now I'm going to plot 1, 2, 2, 4, 3, 8. This is our first example of a nonlinear graph. I think it could be difficult sometimes. We're so used to connecting lines. You kind of have to get good at this, connecting with a nice smooth curve. -1/2. This is where we start approximating. Okay, so let's try to connect this with a nice J shape. Let's see what we got. All right, and we have our exponential graph. So that's f of x equals 2 to the x power. Notice on the left-hand side, I have my arrow. We talked about, hey, make sure, we don't want to make this pass through the x-axis. There's actually going to be no value. I'll briefly give you a preview of what we're going to talk about tomorrow. Think about if we were to hit the x-axis. The x-axis is where y equals 0. Is there any value where you can raise 2 to some power and get 0 as an answer? I'll let you think about that one for a little bit, and we'll talk more about that tomorrow. That's why we don't want to hit the x-axis, because of this dilemma right here. You see my pen stuttered a little bit as I was on the right-hand side, but you want to do a nice smooth curve. Why do I call this a J shape? If it's a little bit of a slanted J shape, but traditionally has that look. And that's our exponential graph. So if you remember on that second slide, there's two sketches of what an exponential graph could look like. And what's going to make that big difference between what they can look like? When is it going to have that J-shaped look? When is it going to have that backwards kind of J look to it? This all depends on the value of b in your equation, meaning that if you know what you're looking for, you can already tell before you even graph it. If we have a b value greater than 1, that is the base, the value being raised to the x power, or whatever the power may be, it's going to be a J-shaped curve, something that looks like what we just did. Very rough sketch here. If we have a base value less than 1, I'm going to adjust this on the fly here. I'm going to say between 0 and 1, or an absolute value between 0 and 1. It's going to look something like this. Almost like a backwards J. Now let's think about why this happens. I think it's very obvious on the left if we have something like 2. If we keep multiplying by 2 over and over again, the values get larger and larger, right? Like on the last slide, 8, 16, 32, it starts getting steeper and steeper. If we look on the right, if we take something like a fraction, like a half, what happens when we keep repeating by a half over and over again? We're actually getting smaller and smaller as x increases, because really we're dividing by 2 when we multiply by a half. Again, let's just say randomly chose it. So any fraction between 0 and 1, not inclusive. 1 itself, notice, is not included on the left and right. Doesn't say b can equal 1. Why is that not an exponential function? Why do you think this is not an exponential function? No matter what I raise this to, what's the answer always going to be? Even 0? It's always going to be 1. So this would actually just be a horizontal line through 1. Looks like an exponential function to someone that doesn't know what they're doing, but that's why we don't include 1 in this definition. So this is the deciding factor. I've seen a lot of questions where you can often, if you know this fact, pick out a matching graph, or you could eliminate some choices just based on knowing this fact alone. All right. On this slide, we're going to take a look at writing a function rule given a completed graph. If you notice, we have a J-shaped graph here. I'm going to start by writing our generic exponential equation, just like I would for a y equals mx plus b problem, which is f of x equals a times b to the x power. Now what we're looking for are really two things, just like we were with slope and the y-intercept. We're looking for the initial value here. That's your y-intercept, a. And our b value, our base. This is what we call a common multiplier. What's that pattern that you're multiplying over and over again that's making it exponential? So if we find these two things, we can write our rule. Now, unfortunately, we can't visually see the y-intercept. I don't want to have to guess what that is. I know it's a fraction between 0 and 1. I don't know if it's a half, quarter, a third. So I don't really want to just throw out a guess to start this problem. What I'm going to do is pick out the nice points that I do see. I see nice points at 2, 1, 3, 2, 4, 4, and 5, 8. I see a lot of nice points here. I'm just going to write those out, or a few of those out. And what this is going to help me do is find my common multiplier. What's the pattern that's happening between consecutive terms? Very clearly here, if I either divide or just look visually, some cases it might not be a number this easy, like times 2. That's where I'm saying dividing might help you find that b value, maybe if it's a fraction or something, just like with geometric sequences. So in this case, I see that the pattern is times 2. Now this is helpful for a few reasons. One, it tells me my b value, so I'm already halfway there. I'm going to jot that down here. Let's call this function f of x. So I already know my base is going to be 2. So I'm halfway there. I'm just missing the a value now. And then this is actually going to lead me to my a value. I'm going to write 2, 1 again. And now I can work backwards. Remember, the y-intercept is where x is 0. So if I know the pattern moving forward is times 2, I can work backwards by dividing by 2. 2 times. 1 to find the value at 1, which is going to be a half. And a second time to find the value at 0, which is that y-intercept, which is the thing I really want here. And that's going to be a quarter. And that's my function f of x for this graph. It's going to be 1/4 or 0.25 times 2 to the x power. So in short, whenever you're given a completed graph, pick out the nice points. It's not a problem if you can't see the y-intercept. What you're going to do is use the points that you did find, or that you did can clearly see on the graph. Use those to find your common multiplier, and then either work backwards, or in some cases work forwards, to find the y-intercept and what it exactly is, and then put those 2 points together, a and b, to your exponential equation. Thanks for watching this video, guys. Hopefully you found everything helpful. Come prepared tomorrow with any questions you have on this topic. Have a great day.